Hello and welcome to this lecture. In this lecture, we are going to try and visualize these operators on the 2D plane, and we know so much about these operators, right? So, what each operator does, but we will visualize these operators by what it does to a few standard lines or shapes that we use all the time, because that will give you a nice picture of what happens. Okay. So, this is a Desmos illustration. So, to make it better, I am going to go and edit it on Desmos itself. Okay. So, this is what I am doing. Okay. So, there is a bunch of points here. I want you to, these are just to create this figure. I am not going to go into great detail on how this figure got created. Maybe I can do this so that it becomes slightly bigger for you to see. I have created this figure, but here is the important transformation here. So, this f of AB is the linear transformation cos s minus sin s cos s. Okay. So, this is the linear transformation. So, what I am doing here is I have this square here, right, and then I have the diagonal. So, I am going to show you what happens to the square and the diagonal when I apply this linear transformation, the rotation transformation. So, S is my angle of rotation. As I keep increasing the angle of rotation, notice what happens. This is something you can easily picture, right. This is the rotation transformation. So, as I increase my angle, it is rotating anti-clockwise, right. So, this is cos minus sin cos. So, that is the anti-clockwise rotation by S. So, it will keep on rotating as I increase S, and you can see this is the line, right. So, this diagonal line becomes this line, this diagonal line becomes this line becomes this line becomes this line, etc. All lines will go to lines, no, in 2D in R2. So, that is a nice thing to see. So, you can see rotation like this. Okay. So, you can keep on going, but I am going only from 0 to 2. So, this is rotation for you. Okay. So, rotation is very nicely visualized by this shape. Okay. The shape and the diagonal give you a very nice way of visualizing rotation. Okay. So, let us do something else. Let us say we do scaling. Okay. Just scaling. I only want to scale. So, f of AB should just be S times A. Okay. And then G of AB, I will let it be M times B. Now, this M and S are different. So, maybe I should keep it same here. First, I will make M to be 1 and S also to be 1. Okay. So, when M and 1 are so 1, you got both the red and white to coincide. Now, as I scale x more, this is scaling only in x. You can see how it is scaling in x. Okay. It went from 1 to 2, and I can also scale the other way. So, you can see how this shape is changing when I just do scaling in x. Okay. Let me freeze the scaling here. I can do scaling in y. If I do scaling in y, you can imagine how this shape will change, no. So, this gives you a way of visualizing these transformations in Desmos. This is a nice way. You can pick other shapes also. I mean, it gives you good intuition. You can pick some other shape and see how it goes also, but this is a nice shape to illustrate. Okay. So, I may do both differently, right. I can maybe keep S here and then M here. Okay. So, you see what happens, right. Any scaling goes on like that, or I may scale both together, right. So, if I scale both together, notice what happens. Okay. When I scale both together, it is just a proper scaling, okay, right. If I go to 2, you will see maybe, okay, it is just a proper scaling. This also became a square, okay. See, it becomes a proper square, and you can see the diagonals are sort of maintained, they just extend, it scales up like that. So, when the gains are the same, this square remains a square. When the gains are different, you start getting all these rectangles and all that, okay. So, these are interesting illustrations. Let us go back to our 1 here, just to be starting from the basic. Okay. So, I am going to show you one more thing which is very interesting. Okay. So, let us look at A plus S. So, this is 1 on the diagonal, and then I am going to put a S in the off diagonal. Okay. So, let us keep S 0. Okay. So, now if S is 0, see, notice if S is 0, this is just AB, right. So, you are doing in this, you are the identity transform, you are not changing any of these things. Now, as I change S, notice what happens. Do you see what is going on? This is usually what is called a shearing action. Okay. So, notice how you get a shearing action when you change S. So, that is what happens when you have, so this is basically a matrix 1 S 0 1, right. So, it is identity diagonal 1 1, lower diagonal 0, upper diagonal is S. Okay. So, when you do that, so you notice how this guy just shears away. Okay, this is a good way to picture these kind of off diagonal things. Okay, so you can go back and check. So now you can see in this, there is no way you can get more than one eigenspace, right? So the x-axis, nothing happens to it. The x-axis remains where it is, but the y-axis, but there's no other line which will remain by itself. No, there'll be no other invariant subspace. Only the x-axis will be the invariant subspace. Nothing else, because it's shearing like this. There's nothing that will be invariant under this kind of a thing, right? So this is a very nice way to visualize. So you can think about invariant subspaces. What is not changing? What will change, etc. in this thing. Okay. So you can change this. You can make it more complicated. You can make you can make it MA plus B. So you notice if you change these guys now, so these are all arbitrary changes here. So you can see, so this changing, it goes on all over the place. So this is a good way to visualize linear transformations in my opinion. So this is an arbitrary thing, right? It's 1S M1. Okay, so it's as good as arbitrary up to scale. So you can see what a linear transformation will do. It seems to be doing all sorts of interesting actions, right? It's doing some amount of rotation, some amount of shearing, some amount of scaling. Okay, so I think the 2 by 2 transforms are particularly nice, and they can be visualized very, very nicely using this. So it's not wrong to say that most or all maybe, right, linear transformations in R2 pretty much do rotation, shearing, scaling. Okay, so nothing much really changes beyond that. Okay, so hopefully this gave you a sense of that, and in every transformation, once you fix the M, you can see that there may be some lines which will get fixed, and when those lines get fixed, you get an invariant subspace, otherwise you don't. Okay, so this concludes our study of eigenvalues, eigenvectors, and these invariant subspaces. Thank you very much.